Hello and welcome back to Lecture 21. This is part 2 of part 1 of Lecture 21, where we're continuing to talk about the topic of relative simultaneity. Okay, so hopefully this part of the lecture will be short and sweet because I just want to walk us through a thought experiment. I want us to think about a particular series of questions considering a particular event and then considering the consequence of that event. Okay, so let's get started. Okay, so this is all just one problem, really. You think of it just one, okay, with just multiple parts. So here's the situation. Supernovas, an example I've used before because I had this thought experiment on my mind. Labeled L and R, L for the supernova on the left, R for the supernova on the right. They occur on opposite sides of a galaxy at equal distances from the center. The supernovas are seen at the same instant on a planet at rest in the center of the galaxy. A spaceship is entering the galaxy from the left at a speed of 0.99 c, 99.9% the speed of light. And that's relative to the galaxy, okay, of which the planet is part of. Okay, all right. So, according to the astronomers on the planet, were the two explosions simultaneous? Explain why. Okay. Well, yes. But why, right? Maybe our intuition tells us that. Well, the stars are equal distance. The former stars are equal distance from the planet. So, the light from those two events of the supernovas would take the same amount of time to travel from each. Okay? So the light would arrive at the same time from both stars, and the planet would know how far away both those stars are. Okay? So here's just the planet. And the light arrives at the same time. That's how we know that they're simultaneous events. So I want to quickly speak to that. I have equal distance and arrives at the same time, right? Those are the two things we know for sure. The distance we know for sure, okay? We know how far away something is. In the real astronomical world, that can be measured. There are certain ways to measure distances to know independently how far away they are. That's the case here. Okay? So, and again, I guess I stress that because I don't want us to think that we just don't know where objects are and we're fooling ourselves into thinking something simultaneous. Because that could be the case, couldn't it? Right? Star L could just be further away. So you could say, oh no, the planet's wrong. No, the planet is right. The two events are simultaneous. Okay? They have enough information to say that with confidence. So, which supernova, L or R, does the spaceship crew see first? See first. Okay? Let's just observe. Again, the spaceship's not full of dummies, or it's not full of people that don't have sophisticated devices for measuring astronomical distances. That equipment is on board the ship. Okay? But anyway, the ship sees L, sees supernova L first. Okay. Did the supernova that was seen first necessarily happen first in the rocket's frame? Okay, well, this is what I was getting at. No. Since L is closer, the light could have just taken less time to arrive at the ship. And instead of saying could, I'll say would have just taken less time to arrive at the ship. Okay, why is that important? Well, because again, that just because two sources reach you at the same time, don't reach you at the same time, I should say, doesn't mean that one happened before the other. I mean, Think about a firecracker, okay? Or watching the fireworks on the 4th of July. You see an explosion in the sky, and you say, oh, okay, look, firework blew up. It was a few hundred meters away, and I saw the light. The light essentially reached me simultaneously. You're like, okay, so that means that event happened. Well, a week later, there's big news, and turns out a huge supernova happened, and it's visible in the night sky and the daytime sky. It's nearly as bright as the moon. We'll be able to see it for months. Big deal. Well, that means that light in your world came later. So then would you determine that the supernova happened later than the firecracker as a separate events? Of course not. The supernova is many light years away. That light took years to arrive here, maybe thousands of years. The event happened a long time ago. So that's not special relativity. That's just travel time for light, just like travel time for sound. There's nothing unique about that phenomenon compared to other waves. Okay. So, part D. Is two light flashes reach the planet at the same time in an event? To help you decide, because you arrange for something to happen only if the two light flashes from opposite directions arrive at the same time. Explain. Okay? So first of all, yes, it is an event. And we know because a device could be built that would only trigger if two light sources were received simultaneously. Were received simultaneously. Hopefully you believe that. I'll just briefly speak to it. It'd be something like, like maybe two little light sensitive circuit elements. They're both going to send a signal and then, a certain amperage. And then there's then something else like maybe an inductor that will create a magnetic field, and the strength of that magnetic field will only correspond to a certain number if both currents run through the inductor. And then that number then would be big enough to cause a light to flash, right? The response to that particular magnetic field. But if only one of them fired, then there'd be less current, and then not enough magnetic field, and then the other light, then the light wouldn't trigger. So so this is an event. The light triggering from both signals in your circuit flowing simultaneously is an event. It either happens or it doesn't. Okay? So, if you answered yes to part D, which we did, then the crew on the spaceship will also determine from their measurements that the light flashes reaching the planet at the same time. Experiments in different reference frames may disagree about when and where an event occurs, but they all agree that it does occur. So again, the light waves arriving simultaneously on the planet is an event. It's irrefutable. It must have happened in all reference frames. Got it. Okay. Now, also both the supernovas blew up. It's not like in some reference frame one of the supernovas never happens, right? So we agree on that. We have three events really now. Supernova L exploding, supernova R exploding. Both waves reaching planet in the middle of the galaxy at the same time. Okay. So, follow along here. The figure below shows the supernovas in the spaceship's reference frame with the assumption that the supernovas are simultaneous. The second half of the figure is a short time after the explosions. Draw two circular wavefronts on the second half of the figure to show that the light from each supernova, or show the light from each supernova. Neither wavefront has yet reached planet B. Be sure to consider the points on which the wavefronts are centered and the wave speeds of each wavefront. Okay. So this is what it looked like. So here is how far we've gone, right? So notice this distance. And the distance, now let me actually show it. Okay, so this, right? That's how far the supernova has moved towards the spaceship. In other words, from the point of view of the supernova or from the point of view of the spaceship, this is how far, this distance right here, the spaceship has moved in a certain amount of time, right? Some time later. Okay. Okay. So that means that from the source, okay, that the wave is going to be traveling out, the source being this here, and the wavefront would have had to travel just a little bit greater than that. Because if you think about it, this spaceship is traveling really close to the speed of light. The light itself is traveling at the speed of light. So the radius of the wavefront from the original supernova is not going to be that much bigger than that radius right there. I'll draw more like that radius. So it will look like this. Okay, so we'll center it. Okay, and I'll center it along. So essentially this is the light that's coming from the supernova. But that, of course, that light didn't exist at time 0, but time t prime later, the light would have traveled like that. Okay? And again, this is supposed to be centered right there. And that's the center of the circle. So you see how the wavefront is just slightly in front of the supernova remnant relative to the rocket? Well, yeah, that's because the rocket's nearly traveling at the speed of light. Okay, all right. Same thing for the light wavefront from supernova 1. Okay, and this is assuming the two events are simultaneous. Okay, so that's good. I'll just copy it. There we are. Yes, it's supposed to look the same relative to the explosion. That's what this is, by the way. This is like a cloud, right? It's the supernova, superheated gases spreading out into space, right? Okay. So, take a look at that. Okay, make sense? Seem like we drew it correctly? Good. Okay, so according to your diagram, are the two wavefronts going to reach the planet at the same instant of time? Okay, well, the planet moved too, right? The planet would have also moved relative to the spaceship the same distance, right? So they, like basically this distance, this one here, all those distances are the same. Yeah, of course they are, right? Because they've all moved towards the spaceship. It's a straight line. So no, yeah, no way. The planet has less, or the wavefront relative to the planet has less distance left to cover, right? So that wave is going to get there first. This one has a much bigger distance. Okay. Oh yeah. All right. So no. The light from supernova L is going to reach the planet first, and the light from supernova R is going to reach later. Okay. So no. The wavefront, like a ripple in a pond, on the left, that's the one from supernova L, will reach the planet first. Okay, and that's because, just to be clear, the planet is moving towards the wavefront. Really. That wavefront, that one being the one on the left, that wavefront, and of course away from the one on the right. Right? At V equals 0.999c. Because the wavefronts, okay, the wavefronts were created at a certain location, and so they're now at rest relative to the galaxy, okay, or I should say they're moving relative to the galaxy at the speed of light, and so, they're just going to continue to spread out into space. So does it seem like we have a contradiction here? Yeah, it does, okay? It does seem like we have a contradiction. But if you kind of aren't sure where the contradiction came from, it came from this here, right? Kind of always a red flag in a problem, especially the fact it's italicized. Assumption. We're making an assumption. Was it a reasonable assumption to make? Yeah, because the waves arrived simultaneously at the planet when that told us that they were simultaneous events. So from definitely irrefutable planet's reference frame, the two supernovas exploding are simultaneous events. But now we're assuming that means they're also simultaneous events for the spaceship. Okay? In the previous video, I told you that that's not the case. So that was a bad assumption, wasn't it? And now we're seeing that, okay, yeah, it's a bad assumption because it contradicts something. It contradicts an event. It makes the event of some device built to be triggered if two light waves arrive simultaneously at it not happen. Because that doesn't happen in the reference frame of the spaceship according to this assumption. Oh, well, that's a problem because events either happen or they don't. There can't be disagreement. Well, then we have to proceed. We have to fix something. So, does our answer to part F conflict with your answer to part D? Yes, because of what I was just saying. Right? The event either happens or doesn't. The spaceship and the planet cannot disagree on the fact that the waves have to arrive at the same time, and our assumption that the events were simultaneous in the reference frame of the spaceship contradicts that event. Okay? So what do we do? So if so, what different assumption could you make about the supernovas in the rocket's frame that would bring your wavefront diagram into agreement with your answer to part D? Okay, your answer to part D, again, being that the two waves arriving at the planet at the same time is an event. Okay, so yes, there is something we could do. We really only have one option. We could assume that the explosions were not simultaneous in the reference frame of the rocket. Not simultaneous. So, okay, is that, a big choice to make, a big assumption to make? Yeah, but did we have any choice in making an assumption? No, and I hope you see that. No, that's the only other option. We have to assume the events were, in fact, not simultaneous in the rocket's reference frame. Therefore, according to the spaceship's crew, the events were not simultaneous. Okay? So no, just to put it in writing one last time, they were not simultaneous, okay? The two supernovas. And to be specific here, it's good, we have to solve problems maybe to answer which one was first and how much sooner did it occur. All right, well, the explosion on the right actually occurs first. So the explosion, well, all right, supernova. On the right actually, again, it's not just perception, occurs first in the reference frame of the rocket. Okay. So, does this contradict cause and effect? No, because an event is a cause and effect. Okay? Events lead to other events. Things happen, something else happens. So no, it does not contradict a cause and effect. But it does say that simultaneity is relative. It's a whole new way of looking at the world.